In this tour, you will explore the cleanroom core of the stem cell instrumentation foundry. So, what is a cleanroom and what's the purpose of one? A cleanroom is a controlled environment where pollutants like dust, airborne microbes, and aerosol particles are filtered out in order to provide the cleanest area possible. Cleanrooms also control variables like temperature, airflow, and humidity. Most cleanrooms are used for manufacturing products such as electronics, pharmaceutical products, and medical equipment. Cleanrooms are classified by how clean the air is. The cleanroom classification requires specific particle count measurements and calculations to classify the cleanliness level of a cleanroom. At our core, we have Class 100 and Classroom 1000 cleanroom. These numbers refer to the number of particles of size 0.5 micrometers or larger, permitted per cubic foot of air. How does a cleanroom work? Essentially, cleanrooms work to remove pollutants, particles, and contaminants from outside ambient air. Outside air is first circulated to a filter system. The filters then clean and decontaminate the outside air according to their specifications. The filtered air is then forced into the cleanroom. Additionally, contaminated air within the cleanroom is forced outside the room by registers, or it is recirculated back into the filters and the process restarts. The fewer particles that are allowed at any given time, the more precautions there are to prevent contamination. Any item which may add contamination or dust is restricted from entering the cleanroom. This includes lead pencils, regular notebooks, papers, cardboard, and more. All users are required to put on full-body gowns prior to entering the cleanroom.
Hi, I'm Praveen Kumar, Technical Director of Cleanroom. I'm going to show you the cleanroom area and provide you information about the cleanroom. In our facility, we have a mask aligner used for UV photolithography, focused ion beam, atomic layer deposition, electrospinning, sputtering, spin coater, wafer rinse station, hot plates, ovens, and dry and wet working stations inside the cleanroom. And we also have profilometer and atomic force microscope outside the cleanroom. Cleanrooms are used to fabricate devices which are used in your day-to-day life or for doing research. One example of such device is a microprocessor in your calculator. Such microprocessor devices are fabricated inside the cleanroom. Most of the electronic devices include deposition and design of multiple layers of different materials. For example, on this mask, we have a design of one layer of electronic chip used in semiconductor industry. To make a device using this mask, we need to transfer this design on a silicon wafer, and that can be accomplished with photolithography. Photolithography is the process by which patterns on a material can be defined using light. It is the means by which small-scale features are created. Photolithography utilizes three basic steps to transfer a pattern from a mask to a wafer, and those are number 1 coating, number 2 exposing, and number 3 developing. We coat a photoresist using a spin coater. A photoresist is a photosensitive polymer. Then we expose the deposited photoresist using a UV light through the mask. We are using a positive photoresist. That means the area which are exposed to the light gets soft and dissolve easily in a solvent called developer. And you can see that the pattern is now printed on a silicon wafer. Now we can use Nikon microscope to perform analysis of the deposited pattern. We also have Bruker's profilometer in our facility. We use profilometer to measure the gaps and the step heights of the features fabricated on the devices. The profilometer can also be used for surface morphology studies of any sample with nanometer resolutions. The other instrument we have is focused ion beam, FIB. FIB resembles scanning electron microscopy. In FIB, a beam of ions is accelerated with high voltage and guided towards the samples. The FIB can be used for etching the material and making patterns with high precision and accuracy. FIB is used for getting high resolution images. The image on the screen is the silicon edge. In addition, we have capability to deposit and pattern platinum metal. FIB can pattern devices with micrometer accuracy. To give you an idea of what micrometer means, here is a FIB image of human hair, which is about 30 micrometer in diameter. Then this is an image of device etched with FIB, and you can see the features are patterned with a thickness of 0.3 micrometer. And this is an image of platinum deposited using FIB. The height of deposited platinum is about 4 micrometer. Sputtering is a thin film deposition manufacturing process. On an atomic level, sputtering is the process whereby atoms are ejected from a target or source material that is to be deposited on a substrate such as a silicon wafer. The sputtering is initiated by the bombardment of the target by high energy particles. For highly pure coating, we need a clean environment. That's why sputtering is carried out in a vacuum chamber. In our facility, we have platinum and copper targets. This system is capable of depositing oxide and other metals. Here you see plasma of platinum, and this can eventually be deposited on any wafer. Atomic layer deposition (ALD) is a wafer phase technique used to deposit thin films onto a substrate. The process of ALD involves the surface of a substrate being exposed to alternating chemical precursors which do not overlap but instead are introduced in a sequence until desired thickness is achieved. ALD offers exceptional conformality on high aspect ratio structures, thickness control at the angstrom level, and tunable film composition. Typically, ALD processes are conducted at the modest temperatures less than 300 degrees centigrade, and the quality of the growth depends upon chamber pressure and temperature. ALD processes require clean environment and performed in a vacuum chamber. ALD has wide range of applications in semiconductor industry, lithium-ion batteries, and solar cells. Atomic force microscopy (AFM) is a surface scanning technique that has sub-nanometer scale resolution. AFM use a laser beam deflection system where a laser is reflected from the back of the reflective AFM lever and onto a position sensitive detector and use feedback loops to generate data of interest. AFM is used for non-destructive surface studies. AFM provides a resolution 1000 times better than optical microscopy's resolution limit. AFM is most commonly used for imaging surface topography. AFM can also be used for surface manipulation using tip forces and to measure the forces between the sample and the probe. AFM can be operated in 3 modes, namely contact mode, non-contact mode, and tapping mode. AFM can be used on hard as well as soft materials. Thank you.